We have already discussed some of the type of the first-order differential equations solutions. First was separable variable, then we take the homogeneous one. In homogeneous, we just make the substitutions and make it separable variable. Then the last lecture we discussed special type of substitutions, and then we just change it to separable form, and then we solve it. The last example I told, we have a non-homogeneous equation, we make it homogeneous, and then we make the separable variable and we solve it. Now today's discussion is about the exact equation. Exact equation, we have to understand it, that we having the equation of the form mxy dx plus nxy dy equal to 0. This is our differential form. We say we can say it exact if there is a function fxy whose total differential is equal to this one, or we can write that df is equal to mxy dx plus nxy dy equal to 0. Here we having this, we take an example, that's 3x squared plus 4xy dx plus 2x squared plus 2y d 2x squared dy equal to 0, and we say is exact. Why it is exact? Because the total differential of this function. So the function I am having here is my fxy, xy is equal to x cube plus 2x square y plus y square. Now the total differential we say df, and you have studied it in your calculus, then df is equal to partial f by partial x. We take the partial derivative keeping y is constant into dx plus partial f by partial y into dy. Now I take the partial derivative of this one. What's my partial f by partial x? I take y is constant, only x is changing. So get here 3x squared. I get here plus 4xy. Is y is constant, y is not changing, this is equal to 0. I take partial f by partial y. Now my partial f partial y, x is constant 0. Then here I get 2x squared. Then with respect to y, I get here plus 2y. So this is my equation 1. I'll come back to this one. This is my equation 2. I substitute here. I get here my df is equal to partial x, that is equal to 3x squared plus 4xy into dx plus partial y, that is 2x squared plus 2y into dy. This is my df, and it's my total differential. We can write it in the form of the total differential as I mentioned here. So then this is, we say, is the exact differential. So this is exact differential equation. So this equation, when we write here, this is equal to 3x squared plus 4xy into dx plus 2x squared plus 2y dy equal to 0 is exact differential equation. Now that's give me df is equal to 0. If I integrate this one, integral of df is equal to 0, that here fxy is equal to constant. When I say this is the exact differential equation, then I'll get here a solution. Then the steps are how we find the solution, and moreover I will say that if we haven't given a differential equation, this differential equation is given to me, how I can say this is my exact differential equation. Now for this E1, we take the derivative of this once again, and write here derivative of E1 with respect to y. So we're having here E1, and we can say we can get here with respect to y, we get here partial 2f over partial y partial x is equal to respect to y. This will be 0, and here with respect to y we get here 4x. This is my E3. Then from E2 I differentiate with respect to x. This one, so get here partial 2f over partial x partial y with respect to x. What I'll get? This will be 0, I get here 4x. So here we can see that in this case, in these equations for 3 and 4, what we get? We'll get here, this says they are equal. And if we take this as m, This is partial m by partial y, and this is n partial x. They are equal. So I will just rewrite this one. So the idea is the second partial derivatives of the functions, they become equal. This one with respect to x. If I write this is my mxy and this is my nxy, and just take parallel to this equation, this is mxy into dx, nxy into dy. This is my mxy into dx, and here is my mxy into dx plus nxy into dy equal to 0. So this is my mx. So this is here when I get it. So I can write here, this is my partial m by partial y is equal to 4x, and partial n by partial x is equal to 4x. So here differentiate respect to y, this will be 0, this is 4x. Respect to x, which differentiate is 4x and y. So we have here partial m by partial y is equal to partial n by partial x. Indirectly, we get here the criterion that the equation will be exact when this is being fulfilled. Exactness test we take here, just defined it. How we can take the equation as exact. So as I explained, we are having here given the differential equation in differential form, mxy dx plus nxy dy is equal to 0. We take partial m by partial y and partial n by partial x. We say if they are equal, then we say then the differential equation is exact. So this is the criteria if this is going to meet, and we can have this example. Already we have done this one. We're having this example. I just leave that one and take another example to show this one, that we're having here the equation as 1 plus ln of x plus y upon x into dx plus here we are having plus ln of x minus 1 into dy equal to 0, where x is bigger than 0. So I can see here, what's my mxy? My mxy is equal to 1 minus 1 plus ln of x plus y upon x, and my nxy is equal to ln of x minus 1. Just to remember it, this is with respect to x, so we differentiate with respect to y partially. With respect to y, we differentiate this one, and with respect to x partially. So we have partial m by partial y. This is 0, this is 0, and we get here 1 upon x. Derivative of y is 1. Then partial n by partial x. So we can get this one with respect to x, this is 1 upon x, that is 0. So from here we get partial m by partial y is equal to partial n by partial x. This implies the differential equation we are going to deal is an exact differential equation. So we take another example, and I try to show that one, how I can just also see that the differential equation is exact. I take here the example. My example is 2 plus x square y into dy by dx plus x y square equal to 0. I write in the differential form, multiply by dx. I get here 2 plus x square y into dy plus x y square dx equal to 0. I compare it to my standard equation, that's xy dx plus nxy dy is equal to 0. The coefficient of x is my m. So my mxy is equal to xy square, and my nxy, the coefficient of dy, that's 2 plus x square y. Now find here partial m by partial y, this equal to 2 xy, x is constant, and then I get here partial n by partial x, derivative of 2 is 0, and having 2 xy. So we can see here, this is, we get partial m by partial y is equal to partial n by partial x. This implies the differential equation is exact. Now we know that how we can check the equation is exact differential equation or not the exact differential equation. Once we find the differential equation exact, the next step is we'll discuss the method how to find the solution of exact differential equation. I have given you one idea here that the differential equation is exact. Then we having df is equal to 0 because it's a function of xy. This will be our solution. When you solve it, this will be our solution. So when this is 0, this means we integrate it to get fxy equal to a constant c. So when exact, inshallah, we're going to discuss it. And remember this relationship. We're going to use this relationship to find the partial f, partial x, partial y. That's our m and so n, and we use this one.